Okay, there's two more reactions, kind of obscure ones, but we're still going to talk about them in chapter 25, and then we'll move on to chapter 26. But we're still talking about carboxylic acid derivative reactions. So the two topics that we have left are Hofmann rearrangement and what is called the Curtius rearrangement. So in the Hofmann rearrangement, what you have is you're going to take the amide, and it's got to be an amide with an NH2 group on the end of it. We're going to treat this with something like bromine, sodium hydroxide, and water, and that's going to basically cause the loss of this carbonyl group to then form simply the primary amine, and we're going to end up forming CO2 in this reaction. So the Curtius rearrangement basically has the loss of this carbonyl group and the R group then moving over and being attached to the NH2 group. So a specific example of this would be, let's say we have this amide, and we treat that then with the bromine, hydroxide, and water, and we would end up then basically forming ethylamine as the final product, plus then carbon dioxide. So we've lost then this carbonyl group in that reaction. Now the mechanism for this is kind of extreme, but what's going to happen is that we are going to start with deprotonating the amide. And I know that nitrogen isn't very, well, the nitrogen itself isn't very basic, but what will happen is the hydroxide can come in and it will grab that hydrogen off the nitrogen, and we'll end up forming then a negative charge on that nitrogen. Now, the reason that that nitrogen actually turns out to be stable as a negative charge is because I can move this pair of electrons and I can basically draw a resonance structure where I can have the O then having the negative charge and the double bond to the nitrogen. So that's the only reason that the nitrogen is that compound is stable, that anion is stable, because it has two resonance structures. Now what will happen then is that we can reverse that resonance structure, or we can just have the N- react with a bromine. It's a little bit different than what we've done in the past. So we could have, for instance, the bromine, the molecular bromine. We can either say, you know what, let's take this N-, react it with the bromine, have that pair of electrons move. Or you can do the same thing by saying, and I'll just write a new bromine over here. You can have this pair of electrons move back down, and then sort of have the CN double bond react with the bromine. That's something we've seen in the reactions of alkenes with bromines that we did last semester. So either way, what you're going to end up doing is you're going to end up forming the nitrogen-bromine bond. Okay, and then what will happen is that the hydroxide can remove the second hydrogen on the nitrogen, and then have that pair of electrons move like so, so that what we do is we end up then with the O-, the double bond to the nitrogen with now the bromine attached, and we end up with that basic intermediate. And now what can happen is we're going to form what is called a nitrene, which is an extremely reactive species. So we're going to bring this pair of electrons back down and then give the pair of electrons to the nitrogen and kick the bromine off. So we're going to end up with the double bond, but now we're going to end up with the nitrogen having two unpaired electrons, and its formal charge would be 1, 2, 3, 4, 5. It would have a 0 formal charge. The problem is that nitrogen only has 6 valence electrons, so it's extremely reactive. And what will happen in this case is that the R group here will take its pair of electrons and it will migrate. So this is kind of like what we would call an alkyl shift, right? We saw this with hydrogen shifts or with methyl shifts. So we're going to have that alkyl group then shift over to the nitrogen. And what we'll end up forming then is we'll have a C, the C double bonded to the O. And then as we move that pair of electrons to the nitrogen, this pair of electrons can be used to form a double bond. So we'll have a double bond to the nitrogen, and then we'll have our R group there with one lone pair left on the nitrogen and 2 lone pairs on the oxygen. And this compound is pretty stable. It is what is called an isocyanate. And isocyanates are actually used to make things like polyurethanes. So if you have like a polyurethane foam or anything that's made of polyurethane, that is made by using isocyanates. So once we have that isocyanate and the R group has migrated, then we have to go through and actually lose the carbon dioxide. So if we rewrite that structure, so I'm going to have the R attached to the nitrogen, doubly bonded to the oxygen. The attached to the nitrogen, doubly bonded to the carbon, which is then doubly bonded to the oxygen with, again, lone pair, just putting it in a slightly different format. Now what's going to happen is the hydroxide is going to come in and add to the carbon, much like what we've seen with any of our reactions that involve like a carbonyl group. Then this pair of electrons will go to the oxygen. So we will form then, we'll have a C with an OH group on it, and we will have the O with the lone pairs, 3 lone pairs now, so it would have a negative charge. And that carbon then is actually not in a particularly great position because it would have a positive charge. So what we could end up doing is we could end up we'll still have the double bond to the nitrogen, so it's actually not a carbocation. All right, so then what will finally happen is the following. Carbon-nitrogen bond is going to be used to grab the hydrogen from water as this pair of electrons then moves to reform the carbonyl group. So what we'll end up doing is we'll end up now with the nitrogen picking up a hydrogen and then reforming the carbonyl group and forming then the OH, and we'll end up with a hydroxide. So then in the final step, what will happen is that the hydroxide that was formed will come in, grab this hydrogen, pair of electrons will move this way, and then that pair of electrons will go to the nitrogen. So that what we end up doing is we end up forming the carbon-oxygen double bond, and as far as the nitrogen goes, it's going to have an extra pair of electrons on it, and it will have a negative charge, which will then, because it's an N-, a strong base, will deprotonate the water to then form the final product. So that we form the amine. So the key steps in this mechanism in the Curtius rearrangement are when we form the isocyanate up here. When we form that isocyanate, we have migrated we have shifted the R group from the carbon to the nitrogen, and then that sets up the loss of the CO2 to form the final amine product. So that is a Hofmann elimination. That's a Hofmann elimination mechanism. And again, it has some newer steps that we haven't seen, but ultimately the key thing to remember is that when you have this unique set of reagents, and it really is, that in the Hofmann rearrangement we're going to lose the carbonyl group, and we're going to end up then just forming the primary amine with the R group that was over here directly then attached to the NH2 group. So that is Hofmann rearrangement in terms of the reaction with amides. The other reaction is what is called a Curtius rearrangement. And the Curtius rearrangement is essentially going to do the same thing, except what we're going to do is we're going to start with an acid chloride, and we're going to react it with our N3-, which remember was azide. And we did this back in the reaction. We did an SN2 reaction of azides and then reduction to form primary amines. So in this case, what's going to happen is N3- is N double bond N double bond N with pairs of electrons there, a -1 charge on each of the N nitrogens, and a positive nitrogen on the center. So reacting this with an acid chloride is like reacting any negatively charged nucleophile. The N- is going to come in, add to the carbon, and we're going to end up then forming the O- with the Cl, and then our N double bond. This will have one lone pair. So we'll end up with a positive charge on the middle nitrogen and negative charge on the N nitrogen. So we'll make this species. And then this pair of electrons wants to come back down and reform a carbonyl. It will do so and we'll lose the chloride. So that what we'll end up doing is reforming the double bond. But now we will have the nitrogen double bonded to the nitrogen. Double bonded to the nitrogen. The negative charge there and a positive charge there. So we'll end up forming this, which the textbook calls an acyl azide. All the acyl term means is that there's a carbon-oxygen double bond in it. So then what's going to happen is then we're going to heat this. So I'm going to rewrite this down here, and we're going to go ahead and just simply heat that acyl azide. And I'm going to have to remind you that this molecule has a great leaving group in it. It has that nitrogen gas molecule, which is basically going to act as a leaving group. So in this case, what's going to happen is that I'm going to move my pair of electrons so that I can form the nitrogen gas. And the way to do that is to basically write the resonance structure of this, which would be to bring this pair of electrons here and bring this pair of electrons there. So I'll put this in a form that it'll be a little bit easier to see how the nitrogen gas is lost. The nitrogen attached to the carbonyl has two lone pairs, and then there's a triple bond between the nitrogen in the middle and the nitrogen on the end. That puts the negative charge here and the positive charge still on that nitrogen. But now it's set up so that now the nitrogen gas can become a leaving group. And so what I'm going to simply do is I'm going to simply break that pair of give that pair of electrons to the nitrogen. I'm going to end up forming then, and I'll write the exact structure out, N2 gas, and then I will also end up with the nitrogen on the end now having the two lone pairs. And again, there's no charge there because the nitrogen has 6 electrons, but having that 6 electrons means that it is very electron deficient, and this is our new friend, the nitrene. And just to go back and review that, when we did the Hofmann rearrangement, we ended up forming this nitrene, which I did not write, I should have. We ended up writing that nitrene, which I should spell correctly. That was this species with the 2 nitrogen, or with the nitrogen having the 2 lone pairs, that then underwent an alkyl shift to form the isocyanate, which then reacted with the base, or reacted with water, and then it ended up losing CO2 in this mechanism. For the Hofmann rearrangement, at this point, in the Curtius rearrangement, we are now at this point, and then those steps that this will undergo are the same. Those are going to be the same steps as Hofmann, as the Hofmann rearrangement. So I won't write those because they are on the previous slide. So Curtius rearrangement is a little bit more preferred, as the textbook says, simply because it doesn't require a lot of heat. You can do this under milder conditions. You just have to react the more reactive acid chloride with azide in order to then make the Acl Azide, which will lose nitrogen gas. And so in the final product, these are going to give basically the same product. So if I'm move up another slide here. So if I'm taking this acid chloride and I'm going to react it with the N3 minus, and we're reacting water, but then again, the azide, sometimes you'll see it written in the book as N3 minus. It just needs a counter ion. So you dissolve that in water. You react the acid chloride with that, and because of the Curtius rearrangement, what I will end up doing is I will end up with this alkyl group then attached to an NH2. So in essence, with the Curtius rearrangement, I have also lost that C double bond O, same as the Hofmann rearrangement. So both of these react and go through nitrenes and then isocyanates to give you that final product. And basically what you have is a migration of, once you put the nitrogen group on there, you have a migration of this alkyl group over to the nitrogen. So both of them would give the same product. Again, the advantage is that an acid chloride will react under milder conditions. And just to remind you that if I wanted to make my acid chloride, I would start with the carboxylic acid and then either react it with SOCl2 or a PCl3 or PCl5. So acid chlorides are easy to make from the corresponding carboxylic acids. So that is the last of the topics in chapter 25. What I've done in the rest of the slides is I have cut and pasted from the Top Hat textbook sort of the summaries of all the reactions, all of them that we've done in this chapter in terms of all the different conversions. So this is sort of a summary of all those different reactions and how you can interconvert one into the other. There are other reactions here, such as with the anhydrides, with the esters, and then also then with the amides, how to make them, how to reduce them, and then also with nitriles, their reactions as well as their reductions. So all of those reactions we've talked about, and they're all kind of summarized here. Okay, so that's going to end chapter 25, and now we're going to move into the last chapter, chapter 26, that we will do this semester. And this chapter is going to involve some what are called Enolate Chemistry, and there's a lot of reactions, and we'll do these over the next 2 or maybe 3 lecture periods, depending on how far I get each time. But we're going to talk about a new kind of reaction that we haven't done. So let me start out by saying this. Let's take this aldehyde. Okay. So if I have that aldehyde, remember all the different reagents that I added to that aldehyde. I added things like water. I added things like alcohol. We've added Grignards, right? We've added Grignards. We've added H- with lithium aluminum hydride or sodium borohydride, or our diballs, or our lithium triterbutoxy aluminum hydrides. We added all these different reagents. And when we wanted to add water or alcohol, we always did that by adding H plus H2O, or adding H plus and the alcohol. Now, one of the things that I didn't say at the time, but that you might have thought is, well, wait, what if I took my aldehyde and I reacted it with something like CH3O-? I mean, I can make alkoxides. The traditional way is to take your alcohol and react it with something like sodium metal. We also know that you could react that same alcohol if you wanted to make the alkoxide. Again, I'm kind of reviewing here, but you could react it with a C-, an H-, or an N-. Why didn't I do that? Because wouldn't that alkoxide just come in and add to the carbonyl and have the pair of electrons move up like that? No. The reason that we didn't do it back then was because that's actually not what happens. And so what actually happens is our chapter on enolates. So what I'm going to do is explain exactly what happens. So what happens is that when you take an aldehyde or a ketone, so I'm going to go back to saying that can either be an aldehyde or a ketone with an H or an R group. When you react that with an alkoxide base, and I'll talk about a little bit better bases that have been used since probably the 1950s and 60s that have really allowed this chemistry to become very popular. Well, I guess now in the last 50 years. But what actually happens is that we do a deprotonation reaction. Okay, so what does that mean? Let's talk a little bit about terminology here. The carbon next to a carbonyl group is called the alpha carbon, and then it goes down the line beta, and we would have gamma and delta. Now, this is a little bit different terminology than what we've used in the past, because remember that if we had a carbon attached to a leaving group, that we called that the alpha carbon, and then the carbon attached to it was the beta carbon, and then we had the beta hydrogen. So I'm changing the alpha beta terminology a little bit here, so that when we have a carbonyl group, the carbonyl is not alpha, the carbon attached to the carbonyl group is the alpha carbon. Okay, so that's the terminology I'm going to use when I say this alkoxide is going to come in and it's going to deprotonate that alpha hydrogen. And when it does, what I'm going to end up doing is forming the negative charge on the carbon. And I'm going to leave this as an aldehyde, but it could be a ketone as well. And this is actually what is called an enolate ion. Now, an enolate ion has a resonance structure. So I can bring this pair of electrons here and give that pair of electrons to the oxygen. We kind of saw that in the last set of reactions, Hofmann and Curtius, how we could do that. So the resonance structure that it can form would have a double bond to the carbon and then an O- with the 3 lone pairs on the oxygen. Now this is, if you're saying enol, what's an enol? Remember that an enol was a carbon with a double bond attached to an OH. That was our enol from previous, well, our enol that we formed way back at the beginning of the semester when we react an alkyne with H plus H2O. And enols weren't very stable. Now, if you deprotonate this enol, you make an enolate. And so when we've talked about alcohols, when we deprotonate an alcohol, we make an alkoxide, another synonym for the oxide to indicate that you have a negative charge is ATE. So this is called an enolate ion. And we will cut through kind of the difficulties here, because what we're going to do is we're going to use this enolate ion as a nucleophile. So we're going to react it with all of the other electrophiles, including other carbonyl groups. You might say, well, what's going to react? The carbon or the oxygen? Which of those two anions is actually going to react in the nucleophile? And we're basically going to use this resonance structure to do our reactions. Is it possible to have the oxygen be the nucleophile and have the oxygen add? Yes, but for this course, C- is going to be our nucleophile that's going to go ahead and react. So that's how we're going to do all these reactions. And unfortunately, I did my PhD work and have done some other things in the area of enolate chemistry, mostly looking at structures and thermodynamics. So I could go on and on about this, but for the most part, we're going to treat the C- as the nucleophile in all of these different reactions that we're going to do. Now, we have a problem. And here's our problem. The problem is, and I've also studied in the past, the acidities of alkoxides versus enolates. And the problem is that when you make an enolate ion, it is roughly the same base strength as the alkoxide that I used to make it. So this is truly an equilibrium when you make the alkoxide. Now, typically the way we make the alkoxide is that we usually mix alcohol and hydroxide, which we also know is an equilibrium, but as that equilibrium produces the alkoxide, that's what's going to do the deprotonation. But the biggest problem that we've had in terms of using enolates as good nucleophiles is simply the fact that we have this equilibrium. And I'll talk about this because this is actually what is called a self-Aldol condensation, but I'll return to that in a few minutes. The issue is that if I only make the enolate not 100% of the time, that enolate, as we're going to see, will react with this unenolized, undeprotonated ketone, and we're going to basically have it react with itself. And that was a big problem unless you wanted to do what is called self-aldol condensations, but it really kind of limited the way that you could use this enolate as a good nucleophile. What we really needed was a way to push the equilibrium 100% and make that enolate 100% of the time and without the equilibrium. Well, this is where the idea of using N- bases came from. If you could develop and use N- bases, then what would happen is that you could react this aldehyde with an N- base, and the reaction would go 100% to the right to form the product, because the enolate and the amide was usually a much stronger base than the enolate was, so it would push the equilibrium to the right. Unfortunately, that's not really a true statement, but I won't bog you down in the weeds, because it is very, very interesting in terms of how this equilibrium gets pushed to the right, because it has to do with the counter ion that we use. But again, I won't go down that road. But needless to say, this is more complicated than what I'm presenting here. Now, typically, one of the big bases that we decided to use, you might say, how about NH2-? Yeah, not a really good one. What we did was we used a lithium amide base, was developed, and to keep the amide from attacking the carbonyl, because remember, N- is a strong nucleophile as well as being a strong base. So how do we stop the N- from acting as a nucleophile and make it only react as a base? Well, how did we do that with tertiary butoxide? We made it sterically hindered. And so when you use a sterically hindered lithium amide base, what happens is this becomes then longer a nucleophile, because these isopropyl groups keep it from reacting. So this is actually lithium diisopropyl amide, because it's got two isopropyl groups, and it's commonly referred to as LDA. So I'll just write out the name. So LDA was one of the first really strong bases that was developed that allowed us to form enolates in 100% yield, and they wouldn't attack the carbonyl as a nucleophile. And I haven't done a lot with LDA. I was a postdoc in a group at Brown where they had done a lot more, and including pioneering how to determine the structure of it. The base that I have used a lot is to actually put two silicon groups on it, and this is called lithium hexamethyl disilazane. And when I was a postdoc, we published papers with lithium and sodium and potassium, and I think we even did cesium, although that stuff might not be published. But we use this as a really nice base to completely deprotonate the alpha hydrogen on the aldehyde or the ketone. We're not going to use these bases in the reactions that I'm going to talk about, because all the textbooks talk about this traditional use of using alcohol and hydroxide to make the alkoxide. But if I wanted to eliminate the equilibrium on all these reactions, this is what I would do. So that's kind of an introduction in terms of making enolates in order to make the that enolate ion. So what happens? Well, let's just talk about some of the reactions that we could do. Some that we already know about. So let's say I start with this ketone, this aldehyde, and I react it with an alkoxide that I formed by mixing alcohol and hydroxide together. And okay, it's going to be equilibrium, great. I'm going to form this enolate. What can I do with that enolate? Well, the first thing I can do is I can do an alkylation reaction. Remember, alkylation means adding an alkyl group. So this is now a nucleophile. So what should I do? Well, let's go ahead and just add a primary alkyl halide to it. And what's going to happen? The C- is going to come in. It's going to kick off the bromine. And I'm going to end up adding then the ethyl group to my alpha carbon. And so I can do an enolate alkylation reaction. And that's a very useful reaction to be able to do, because now I can add any alkyl group. Within reason, this should probably be primary and secondary again. But I can go ahead and add alkyl groups to my alpha carbon, and I can transform one aldehyde or ketone into another, which is a very useful thing to do. Now, I'm going to go back into the ketone aldehyde chapter and talk about enamines for a minute, because you can also do this with enamines and do the same alkylation reaction. So what are you talking about with enamines? Well, here's what I'm talking about. Let's say I took this ketone and I added to it a secondary amine. What is the product I'm going to get? I would end up with this as my product. I would end up with that product. Okay, so this is what we called an enamine. Now take a look at that enamine. It has the same structural feature here of an enol, and I can actually do an alkylation using an enamine in order to alkylate what was the alpha carbon, the one that's next to the carbonyl. And here's what would happen with the enamine. So with the enamine, what I'm going to end up doing is this. I'm going to react this with, I'll react it with my same methyl bromide as I did with the enolate. But you might say, okay, well, where is the nucleophile here? Well, here's what happens. What happens is if you think about taking this pair of electrons on the nitrogen, moving here, then you can take this pair of electrons in the double bond, attack that carbon, and kick off the bromine. So, in essence, what I did was, I'm going to write this in brackets because this really doesn't exist. But what I just did well, actually, you know what? I don't need the brackets because I'll just write the resonance structure here. The resonance structure I could have drawn is this one. The positive charge on the nitrogen, and then the negative charge on the carbon, so that C- then is what's going to attack the CH2 of the ethyl bromide and kick off the bromine. So that makes it a little bit clearer what the nucleophile is. So the product that I make is going to have the CH2, CH3 now attached. And yeah, I'll have this nitrogen now with its positive charge. and its CH3 group here. So I'll end up forming that molecule, and then all I need to do is then give that pair of electrons back to the nitrogen. And, well, before I do that, I'll move that pair of electrons back there. And now what happens? The nitrogen now goes back to being neutrally charged, but now I have a positive charge here. What happens next? Next, the water will come in and attack that carbon. Now let's draw out the gory details here, just as a review. Now what's going to happen, we could shorten this mechanism up considerably by just saying the nitrogen's going to get the H plus from the oxonium ion, so that I'm going to end up with my OH and now my N plus. And what happens next? Next, I'm going to lose the H plus. The ammonium group is going to leave. And I'm going to end up then losing H plus and the nitrogen. So let me just rewrite that structure here. Remember, I added the CH2CH3 group. I now have my O with my H, my N with my H, and my two R groups with the positive charge. I'm just going to rewrite that. So now this pair of electrons goes here. The ammonium groups leave, so I lose basically that whole ammonium ion, and I ended up reforming. Whoop, there's no H there. That's a carbon with 5 bonds. Then I end up with the double bond, the CH3. What am I missing? There. So when I rewrite that structure, it looks like this. And then I'm going to go ahead and lose the H plus, lose the ammonium, so I end up losing NH2R2 with the plus charge. I end up losing that ammonium when the nitrogen gets united with that H plus. So what I end up with is, I end up with carbonyl reforming. So what I just did was I just alkylated the alpha carbon using that enamine. So what I'm showing you here is the idea that enamines, you know, when we made them before, they really didn't have a purpose or a function. They do, and they can be used as sort of enolate equivalents in order to do alkylation reactions and the reactions that I'm going to talk about in the coming remainder of this lecture, as well as the next one or two. This chemistry, this enamine chemistry, was actually it was developed by a guy named Gilbert Stork, who was at Columbia. And actually, Gilbert Stork was the PhD advisor of my postdoctoral advisor at Brown, so I'm kind of familiar a little bit with that type of chemistry. It's basically just simply an equivalent of the enolate chemistry. So the last reaction that I will talk about then is, what else can we use enolates for? And the last thing that we will talk about in this lecture is, let's make a ketone. And for the sake of argument here, let's make the ketone symmetrical. And I'm going to go ahead and I'm going to treat this with a mixture of alcohol and and hydroxide, which is basically going to be the net result is making an alkoxide. The alkoxide is going to come in, and let's make the alpha hydrogen on the right. The O- is going to come in and grab that hydrogen, so that I'm going to end up forming the alcohol, and I'm going to end up forming the enolate. Okay, so I just did what I had done before, is to react the enolate. Another reaction that I can do with the enolate is to add then bromine to it. And what we just saw with a double bond or with negative charges reacting with bromine is the enolate could come down, grab the bromine, kick off the Br-. So I'm doing basically the same reaction that I did when I reacted a double bond with the bromine back last semester. But what I'm now going to do is I'm now going to add a bromine to the alpha carbon. And so this is called an alpha bromo. In this case, this is an alpha bromo ketone. And we'll see alpha bromo ketones are pretty useful, because now that I have that, what can I do with that bromine? I could do an elimination reaction and form a double bond to that carbon. I could react that with a nucleophile and substitute the bromine, so I could put other groups at the alpha position. There's one drawback to alpha bromo ketones, and that is that they are called lacromators. I made these once in my career. I ended up having to put everything that touched it, any kind of paper towels or anything, in a plastic bag and seal it up. Let's see, Alex, things that are lacromators for 100, and I think I've done this in class before. Onions, organic chemistry, things that make people cry. So that is what a lacromator is. So that is going to be the end of the first part of chapter 25. At some point we will do this reaction with the bromine again. It was what is called the Hell-Voldhard-Zielinski reaction, but we will leave it here. So the idea here is that the key part is, let's use a combination of alcohol and hydroxide to make an alkoxide that will then deprotonate the alpha carbon. I will then make an enolate, and right now what can I do with the enolate? I can react it with an alkyl halide, like I did back here. I can react it with an alkyl halide and alkylate the alpha carbon, or in this case, I could brominate that and form an alpha bromo ketone. So next time what we will do is we will react it with other ketones. Then we'll talk about esters, and we'll talk about all of these different reactions that essentially come from the same thing, making the enolate, but now we're going to react it with other carbonyl compounds. Okay. So we will continue into chapter 26 in Top Hat in the next lecture video.